let's explore another example of a binomial distribution. Let's say I'm playing basketball, and I know I'm going to take 10 shots in the game. So I'm going to take 10 shots. Let's say that n is equal to 10. That's the number of shots I take, and let's just say that every shot I take, they're independent events, and that in general I have a 30% shot chance of making any given basket. We're not going to get too detailed of where I take the basket from, or they three-pointers, or they lay out, whatever. Every time I take a shot, I have a 30% chance of making it. So say the probability of success is equal to 30%. Probability is equal to 30%. I just made that definition. And let's define a random variable x, like we always do. X is equal to number of shots I make. Number of shots, baskets I make. And this one's a little bit more interesting than the flipping a coin example, because in the flipping of coin example, heads or tails both had an equal probability of happening. In this situation, making a shot is less likely than not making a shot, right? The not making a shot, let's say not making a shot, that is equal to 1 minus the probability of making a shot, which is equal to 70%. So there's a slight twist on what we did before, but in some ways it might be a more interesting example to your everyday life. And let's see what the distribution looks like. And also I'm taking more shots now than I did before. And so it'll probably take a little bit more time. Actually, this is too much. Because I don't want to waste too much time. Let's say I take 6 shots. And x, the random variable x, is the number of shots I make. So let's think about how we figure out this probability. What is the probability that x is equal to 0? So I make no shots at all. So I take 6 shots, and every shot I take I miss. So in order for that to happen, this event has to happen 6 times in a row. So something with a 70% probability has to happen 6 times in a row. The probability of this is 0.7, right? That's 70% times 0.7 times 0.7 times 0.7. I'm getting confused. It's 0.7 times 0.7 times 0.7 times 0.7 times 0.7 times 0.7, right? Each of these are missing the first shot, second shot, third shot, and so forth and so on. And this is equal to 0.7 to the 6th power, whatever that might be. All right. And there's only one way to do it. I literally have to miss every shot in order for x to be equal to 0. What's the probability that I make exactly 1 shot? So, well, what's the probability? I might make the first one and then miss the other ones. I might miss all of them but the second. I might miss all of them but the third. So let's think about what's the probability of each of those circumstances. So if let's say I make it, I'll call that a make. Too bad make and miss both start with M. Let's see, I'll call it point and miss, right? So it could be like a point and then 5 misses. 5 misses. It could be a miss, a miss, a miss, a point, a miss, a miss. As you can imagine, there's 5 of these scenarios, right? I could just there's actually 6 of these scenarios, right? My point, the shot that I make, would be in one of these 6. I don't want to use the word bucket because we're already using a basketball analogy, but it can be in one of these 6 spots, in one of the 6 shots that I take, right? So there's 6 of these scenarios. But what's the probability of each of these? This is going to be equal. This is a 30% chance of happening, and then each of these are 70% chance of happening, right? So it would be 0.3 times 0.7 times 0.7 times 0.7 times 0.7 times 0.7. This is 0.7 to the 5th, right? Times 0.7 to the 5th. That's the odds of this happening. What are the odds of this one happening? Well, you see, you have 0.7 times 0.7 times 0.7 times 0.3 times 0.7 times 0.7. But if you think about it, you're still taking 0.7 times itself 5 times, right? 0.7, 0.7, 0.7, 0.7, 0.7. You're taking 0.7 to the 5th power, and you have to multiply by 0.3 once as well. So no matter where you make the shot, the chances of any of these permutations independently are 0.3 times 0.7 to the 5th, whatever that is. And then how many ways are there to do this? Well, we just figured out there's 6 ways to do this, right? You might make only the first shot, you might make only the second shot, only the third shot, and so forth and so on. So the probability that x is equal to 1, the probability that our random variable is equal to 1 is equal to 6 times 0.3 times 0.7 to the fifth. And just so that we make it clear and connect it all to the binomial distribution, what would have been the, if we would have done the, n choose 0 here, what's the binomial coefficient? So in our example, n is 6. So what's 6 choose 0? 6 choose 0, that's 6 factorial over 0 factorial times 6 minus 0 factorial. 6 minus 0 factorial. 6 minus 0 is just 6. So 6 factorial divided by 6 factorial, those cancel out. You're just left with 1. Well, what's 0 factorial? And this is one of those bizarre definitional things in mathematics, and I'll leave you to think about it, and I've addressed this in previous videos. But 0 factorial is actually so that it works out properly, is defined to be equal to 1. And I did that to just show you that this is the binomial coefficient on this term, right? So we just multiply it by 1. That's why I never even brought it up. The probability of this happening is 0.7 to the 6th. And then you multiply it times the binomial coefficient. But there's only one way that this can happen, and that's why this turned out to be 1. I didn't want to confuse you, so I didn't bring all of that up. But we did still use the binomial coefficient. Let's think about it in this one. In this situation, we're taking 6 shots, and we're choosing only one of them to be made. What's 6 choose 1? That's 6 factorial over 1 factorial divided by 6 minus 1 factorial. 6 minus 1 factorial. That's 6 factorial divided by, well, 1 factorial we can ignore, that's just 1, divided by 5 factorial. Well, what's that? That's 6 times 5 times 4 times 3 times 1 divided by 5 times 4 times 3 times 1. So everything else cancels out except for just for the 6's. And so that's where we got our 6 from. We got it by reasoning, which actually I think is a better way to get it. But I just wanted to show you that we're still using the binomial coefficients. This is 6 choose 1. And then we multiply that times the probability of any of these permutations happening. And we figure that out by we make one shot and we miss the rest. Let's keep going. I think you'll get the hang of this sooner than later. What's the probability that you make exactly 2 shots? So what's the probability for any given, let's say I miss, and then I get 2 points, or 2 shots. I don't want to get too confused. Let's say they're all worth 1 point, this version of basketball we're playing. So here, what's the probability? If 0.7 times 0.7 times 0.7 times 0.7 times 0.3 times 0.3, right? So this is 0.7 to the 1, 2, 3, 4th power times 0.3 squared, right? That's each of these circumstances, but this isn't the only way that I can make 2 shots. I can pick, essentially I can choose any 2 of these shots I take to be the ones that I make. I'm not picking it, but the gods of probability will pick it, right? So that this isn't the only circumstance. The probability of just this circumstance, where I miss exactly the last 2 shots, is this. But if I wanted to figure out all of the different ways that I can make exactly 2 shots, I would essentially say, well, I'm taking 6 shots, and I'm choosing 2 of them to be made. So how many does that result in? Let's see, 6 factorial over 2 factorial over 6 minus 2 factorial. That is equal to, I like to multiply it out, that's 6 times 5 times 3 times 2 times 1 over 2 times 1. Divided, this is 4 factorial, right? 6 minus 2 is 4 factorial. It's 4 times 3 times 2 times 1. Oh, and actually, I forgot to write a 4 up here. 6 times 5 times 4 times 3 times 2 times 1. Anyway, this cancels out with that. The 2 and the 6 is 3, so it becomes 15. So there are 15 possible ways to make exactly 2 shots, especially if you don't care about the order in which I'm not saying that, this point and this point, if they were to happen the other way around, it doesn't matter. It's kind of the same circumstance, right? It's the same, I made the last 2 shots. It doesn't say I made the second to last shot in one way and I made the last shot in the other way. We're not differentiating between. We're just saying that we made them, right? So that's why there's 15 different ways to make 2 shots out of 6. And the probability of each of those is 0.7 to the 4th. 0.7 to the 4th times 0.3 squared. So the probability of making exactly 2 shots is going to be 6 choose 2 times 0.7 to the fourth times 0.3 squared. And we can go on. Let's do them fast. The probability that I make exactly 3 shots by the same logic. Well, what's the probability that I make exactly in any one of the circumstances? Well, how many ways can I make 3 shots? Well, I'm taking 6 and I'm choosing 3. And then the probability of each of those ways is, in order to make 3 shots, I'm going to miss 3 shots, and then I'm going to make 3 shots. That's straightforward enough, and we could calculate what that is. But hopefully you know it. Let's see, let me just do it. So that's 6 factorial. That's 6 factorial over 3 factorial times 6 minus 3 factorial times this part. 0.7 third times 0.3 squared. Let's keep going. And this should actually, it gets faster once you see. Probability that I make exactly 4 shots. Well, I'm taking 6 and I'm going to make 4 of them. So I have to choose 4 out of 6. So if I'm making 4 shots, I'm missing 2 shots. So there's going to be 2 shots that I miss. 0.7 times 0.7, that's the probability of a miss, 0.7. And then I'm making 4 of them. So 0.3. There's a 30% chance of making each of them. So to make 4, 0.3 to the fourth. So in any one of these ways where I make 4 shots, this is their probability. And there are this many ways of doing it. And that's equal to 6 factorial over 4 factorial times 6 minus 4 factorial, and then times 0.7 squared times 0.3 to the fourth. And if you think of it, this is 2 factorial, right? This is 2 factorial. And we figured out what that was up here. Right? 6 choose 2 was the same thing. It was 6 factorial over 2 factorial divided by 4 factorial. This is the same thing as this. We just switched the 4's and the 2's. So this would also be equal to 15. But anyway, I'll probably do that in the next video. But let's just calculate these really fast. The probability that x is equal to 5, I make 5 shots. That's 6 choose 5 times 0.7. So I'm only missing 1 shot, right? So the probability of missing 1 is 0.7. And then I have to make 5, not necessarily in a row. 0.3 to the fifth. But you see, each of the ways, any given way that I make exactly 5 shots, this is the probability. And there are this many ways, 6 choose 5 ways of making exactly 5 shots. I could get the first 5 shots, miss the 6th. I could get the last 5 shots. I could make the first, miss the second, etc., and so forth. And then finally, the probability that x is equal to 6. I make all of the shots. That's 6 choose 6. How many ways can I pick 6 things out of 6 choices? And there's really only one way. You could calculate it by calculating that. And once again, you'll have to know that 0 factorial is equal to 1. And I have to make all 6 shots. So 0.3 to the 6th, right? 0.3 times 0.3 times 0.3 times 0.3. Anyway, I'm all out of time again. In the next video, we're going to graph this.